Hello, my name is Ishan. Today I am going to discuss Dijkstra's algorithm which deals with shortest distance in a graph. But before going to straight into topic, I am going to tell some general concepts of algorithms. An algorithm is method of representing the step-by-step procedure for solving problem. It is method of finding the right answer to a problem or to a different problem by breaking the problem into simple cases. Algorithm is a step-by-step procedure which defines a set of instructions to be executed in certain order to get desired output. Algorithms are generally created independent languages, and that is, an algorithm can be implemented in more than one programming language. But it must possess the following properties. Finiteness. First is finiteness. An algorithm should terminate in a finite number of steps. Then next one is effectiveness. Each step must be effective. Then we are going to discuss Dijkstra's algorithm. So the Dijkstra's algorithm exists in many variants. Dijkstra's original algorithm found the shortest path between two given nodes in a graph. But a more common variant fixes a single node as the source node and finds the shortest path from the source to all other nodes in the graph, which producing a shortest path tree. Now we are going to discuss through a PowerPoint presentation.
So here we are going to discuss Dijkstra's algorithm, which is main algorithm in data structures and algorithms. Basic introduction of Dijkstra's algorithm. Dijkstra's algorithm or Dijkstra's shortest path algorithm or SPF algorithm is an algorithm for finding the shortest path between nodes in a graph. It is actually discovered by computer scientist Exers Dijkstra in 1956, published after 3 years 1959. It is first computer algorithm in which shortest path between nodes of graph is successfully described. It actually differs from the minimum spanning tree algorithm because the shortest distance path between two vertices might not include all the vertices of the graph in that algorithm, which is spanning tree algorithm. So Dijkstra's algorithm is very useful in modern applications related to computer networks and many. So here we are going to discuss actually how it works. So Dijkstra's algorithms work on the basis that any subpath B to D or shortest path A to D between vertices A and D is also the shortest path between B and D. Watch what it actually states. So there is source and destination, we can call it as B to D, and there is one midway or shortest path between two vertices. So the black line is shortest path, but the green line is subpath in shortest path, which can be shortest path between two sources, between source and destination. So from example we can conclude that each subpath between the path of graph is the shortest path. Scientists Dijkstra use this property in opposite direction. That is, we overestimate the distance of each vertex from the starting vertex. Then we visit each node and its neighbors to find the shortest subpath to those neighbors. The algorithm uses the greedy approach in the sense that we find the next best solution, hoping that the end result is the best solution for the whole problem. Now let's see one example of Dijkstra's algorithm with the help of graph and nodes.
So this is our example. This is undirected graph where source node is 1, which is starting node, and our destination is 6. So we are going to find the shortest distance from 1 to 6. Here we are taking the example of undirected graph. We can do Dijkstra's algorithm for directed graph also. We are considering weight of our nodes source node is 0 and all other nodes are infinity. Here the weight represents the distance between two nodes, and we are going to discuss visited nodes and unvisited nodes both. So we are starting from 1. So we are considering only neighbor nodes, which is 2 and 3. So I mark 1 as visited and unvisited are 2, 3, 4, 5 and so on. So the weight of means distance is 0 and all others are infinity. Again, visited nodes, we can see this is 3, so I am updating infinity to 3, and this is 6, so I am updating this to 6. But during Dijkstra's algorithm, we consider only minimum distance, which is least distance is here 3, so we are considering 2 to be visited. One is also visited, so 1 and 2. Unvisited are 3, 4, 5 and 6. And for visited, for weight, we are considering 0, which is first distance, 3, which is second node distance, and 6. And all remainings are infinity. Now we are considering 2, which is where our starting node. So we are considering only neighbor nodes, and we are not moving back to our first node. So we are considering only 2, 3 and 4. Means from 2 to 3 and 2 to 4. So 5 plus 3 is 8. I am updating this. And 3 plus 2 is 5. So this is less. I am going to update this again. So the least distance is 5. So I am considering 3 to be visited. So 1, 2 and 3 are visited. Remaining are 4, 5 and 6. So weights are 0, 3. Now we updated this, so I removed 6 to 5. Infinity, this is 8, and 5 and 6 are 8 only. So now we are at 3. Now I am moving to this and this. So here you can see 5 plus 2 is 7. I am updating this. And again 8 plus 3, which is greater than 8 obviously. So I am not going to update this. So 1, 2, 3 and 5 is updated, visited. So marking it as visited, and remaining are 4 and 6. So weights are 0, 3, 5, 8, 7. Remaining is infinity. So we are at 5. So again 7 plus 5, this is 12, and this is greater than, obviously this is greater than, because this node is 6 here, so this is always greater than. So we are not considering this. This is greater than 8, this node. So I'm marking it as 1, 2, 3, but it is already visited, means we are already traced. So I'm not considering this, and I'm directly writing 1, 2, 4, 5 are visited, 6 is unvisited, and our distances are 0, 3, 5, 8, 7, and this is 12. Here you can see. So from this example you can see we moved from 1 to 6, and 6 is also visited, which is nothing nodes are remaining, no nodes are remaining here. So 6 is also visited, and we are moved from 1 to 6, and distance is 12. Therefore 1 to 6 minimum distance is 12. I implemented this for undirected graph. Similarly, you can implement it for directed graph also.
So from the example, you understood how these algorithms actually work. So we are going to discuss pseudocode of this algorithm. We need to maintain the path distance of every vertex. We can store that in array of size v, where v is the number of vertices. Second point is, we also want to able to get the shortest path. Not only know the length of the shortest path. For this, we are going to map each vertex to each vertex, and then we are going to last update its path length. Once algorithm is over, we can backtrack from the destination vertex to the source vertex to find the path, which is shortest path. A minimum priority queue can be used to efficiently receive the vertex with least path distance. So here is the pseudocode. So we declare a function which is Dijkstra's, and there is a parameters j and s. So for each vertex v in G, means the graph, the distance should be less than or equal to infinite, and the previous vertex should be null. From the example, we understood why we should put this at infinity. So if v is not equal to s, add v to priority queue, which is q, so distance should be less than 0. The next condition is queue should not be empty. So here we are going to use while loop to execute this. So from this line you can easily understood why we are using this. For each unvisited neighbor of v of u, means the neighbor of any vertex, temporary distance, which is temp distance, it should be distance of u plus edge weight of u and v. If temporary distance is less than distance of v, then we are going to use this priority queue, and we are going to return the distance and previous distance. So here I implemented this algorithm in Python. So for this we need to import this package, sys package. Then I provide the vertices, and then I provide the edges. So to find the which vertex is to be visited next, I created v, I defined a d, and then I run the for loop with index, and then I put number of vertices is equal to length of vertices, and for printing distance I again use for loop. So here is the output. So distance from a from source vertex is 0, means distance from a is the source, to source is 0, and here you can see all the distances. From this you can understood which is least distance, which is shortest distance. So from above output we can easily find the shortest path between source and destination using these distances actually. So Dijkstra's algorithm complexity. For any algorithm we always discuss time complexity and space complexity. Time complexity of Dijkstra's algorithm. It depends on Dijkstra's algorithm. Here I use simple algorithm with time complexity big O v square, where v is the number of vertices. But it can be reduced by efficient manner, and the reduced time complexity will be big O e log v, which is very less. So e is the number of edges and v is the number of vertices. Space complexity of Dijkstra's algorithm. So space complexity of Dijkstra's algorithm is big O v, where again v is the number of vertices. Applications of Dijkstra's algorithm. This is very important point, because in modern problems we always use Dijkstra's algorithm. First one is to find the shortest distance between nodes of any graph. It is a main, or we can say it is a basic application of Dijkstra's algorithm. So from example we understood how it actually works. So we can implement Dijkstra's algorithm for any graph to find shortest distance. In networking applications such as Facebook, Instagram, or your Gmail, WhatsApp, it uses Dijkstra's algorithm. It actually works very complex by using 2 or 3 Dijkstra's algorithms or 2 or 3 other algorithms. Third one is in telephone networks and computer networks, which is very important. Actually, in telephone network, you can see analog digital trunk and IP trunk, which actually uses the Dijkstra algorithm, and IP phones means which are register IPs. So it actually uses the Dijkstra algorithm to find the shortest path between two nodes or two phones, which phone is the node here. So it uses that nodes to find the shortest distance for communicate. And in computer networks, it usually deals with internet connections. So it uses the Dijkstra's algorithm to find the shortest path between two nodes. And here is the node is the computer machine or any other machine which is connected to your internet. Fourth one is to find the locations in the map. So it is modern method, means Dijkstra's algorithm is modern method to find shortest distance between your destination and source. So it's usually deals with Dijkstra's algorithm. So here you can see how it actually works. So this is my source and this is my destination, and it traces through its neighbor vertices and finds the shortest distance. Finally, we are going to discuss the conclusion and the summary.
So the conclusion of our learning is, first one, the code calculates the shortest distance but doesn't calculate the path information. So actually Dijkstra's algorithm calculates the shortest distance but not the path information. So for this we can create a parent array and update the parent array when distance updated, like you know the prisms implementation. Use it and we can use it to show the shortest path for source to different vertices. Dijkstra's algorithm can be used for directed graph also. We discussed the applications of Dijkstra's algorithm. There are much more applications of Dijkstra's algorithm. There are several disadvantages of Dijkstra's algorithms also. First one is Dijkstra's algorithm doesn't work for graphs with negative weightages. For such graphs, we use different algorithm, which is Ford algorithm. The code finds the shortest distance from the source of all vertices. If you are interested only in shortest distance from the source to single target, we can break the loop or for loop when picked minimum distance vertex is equal to target, which is step 3 in the algorithm. And we learned Dijkstra's algorithm, how it works and its effectiveness.